Sharing screen.
All right. I think we're ready. Welcome, everybody, to the first meeting of the Quantum Technology Club for fall 2024. And we're going to start with a quick introduction to quantum computing. And this is really informal. If you want to stop me at any point and ask a question, please go ahead, raise your hand. If you're online, you could break in. Just go ahead and ask something, turn your mic on and ask. So let's get started. Go. This here. No. All right. So you all have, most likely, a smartphone in your pocket. And on the right-hand side here is a picture of ENIAC, one of the very first computers. It's as big as a room, uses vacuum tubes to do calculations, and it has all these wires and such to connect it. And it needs a team of technicians to keep it running because vacuum tubes burn out and they need to change connections and stuff like that. And, you know, it's been a long time, been almost 80 years since ENIAC was created, and we've progressed a great deal. Now we have something that's preposterously more powerful in every one of our pockets. And these days, you could make this entire computer smaller than a dime. This is ENIAC on a chip. That's a 1 microchip with everything that ENIAC has, all on 1 microchip, smaller than the size of a dime. And so, these computers, your phone, ENIAC, this thing on a chip, are classical computers. And the idea behind quantum computing is that it might be able to use the weird properties of quantum mechanics to be as far beyond a classical computer as our phones are, or even our laptops are beyond ENIAC. And I've written here 20 question mark, because it's not really certain when we will have quantum computers that will do the kind of things that we hope them to do. Yes.
Would you reckon that you would have something like that before 2100?
Oh, that's a tough thing to say. That's so far in the future, 80 years. I don't think I could venture a guess.
That's fair.
So many other things could happen between now and then. That this one aspect of human civilization is difficult to know how it would be at that point. Yeah, we can make maybe good predictions for the next 5 or 10 years. So I think the main thing to take away from an introduction to quantum computing is that quantum computing is for special hard tasks. It's not good for everything. Not all tasks go faster or are even possible with quantum computing, even in the imaginary ideal quantum computers that we could think of. So what is it good for? Well, a quantum computer can answer certain important mathematical and physical questions faster than any normal, meaning classical computer, no matter how big. There are some things that a quantum computer could do better than the biggest possible classical supercomputer. And that is why it's really interesting. This was theorized a long time ago, before anybody had any idea how to make a quantum computer. But the sort of math behind it was apparent even then. So there are certain problems that will likely be part of a quantum computer's milieu, including simulating complex quantum systems, breaking encryption, and searching databases. And these are the sorts of problems that, if they're sort of too large, you give them to a normal classical computer, and it could take forever for them to solve it, or maybe they won't be able to. They'll choke on it. Whereas if you give them to a quantum computer, in principle, that you'll be able to do them. You'll be able to do something like simulate the complex quantum interactions between electrons in complex molecules, solve protein folding or photosynthesis. You'll be able to break encryption or search very large databases efficiently. The breaking of encryption was one of the first killer apps theorized for quantum computers, and made it all the big players like governments very, very interested in. because if we could break encryption, that would be super useful. And you also want to make sure that nobody can break your encryption, so you better get there first. Likely, the thing that will be the first task of feasible quantum computers will be to simulate complex quantum systems that are difficult to simulate in any other way. Because what is a quantum computer but a complex quantum system that you have very precise control over? And you could then use it to pretend to be some other complex quantum system. Right? That's what your computer does anyway. You play a video game, it's simulating the physics of that video game, right? You have a complex classical electronic system that is pretending to be something else, Mario jumping. And that same kind of paradigm could be used for a quantum computer to simulate a complex quantum system that would be interesting for various reasons. And that'll bring us to quantum chemistry and biology. You'll be able to simulate proteins like drugs, enzymes, photosynthetic chemicals, catalysts. These are things that enable chemical reactions to happen more easily with less energy, that could reduce pollution, like the catalytic converter in your car, or produce chemicals cheaply using less energy. You could simulate materials before trying to make them for that could be useful for solar energy. So you can see there's a lot of potential applications, even for this first thing, most likely task that quantum computers will be able to do, which is simulating other complex quantum systems. Yeah.
So does that mean that quantum computers are good at simulating any kind of system?
Not necessarily. If your system doesn't have the kind of quantum mechanical interactions between many particles, then it's unlikely that quantum computing will be necessary to simulate it efficiently. And you'd be better off doing something on a classical, maybe a big classical computer, but a classical computer.
Okay.
So the systems have to have some kind of quantum mechanical behavior themselves. A certain flavor of quantum mechanical behavior, let's say. Everything has quantum mechanical behavior, but a lot of those can be simplified in a way that is amenable to classical computation, whereas some others cannot be simplified that way.
Okay.
Oh yes, and then Shor's algorithm, this is quantum enhanced decryption, which is the killer app that I mentioned that was developed in the 90s that really kicked off a lot of interest in this, and Grover's algorithm, which is searching a quantum database. And you can imagine how some group like Google would be interested in that capability. So how does it work? So quantum weirdness makes it work. All the strange things about quantum mechanics makes it work. We're going to go over those. The first one is superposition. So if you're familiar with bits in a computer, they are zeros or ones. But a quantum mechanical bit, a quantum bit or qubit, is not a 0 or a 1, but is some combination of both and neither. It is an indefinite state. That's a superposition state, and that's sort of graphically indicated here by this blue or red or combination of circles. And what that means is that the state of the qubit is not defined until it's measured. It doesn't have a definite value. And a quantum bit can be in a superposition of 0 and 1, whereas a classical bit will always be either a 0 or a 1. There's also entanglement, which you may have heard of. And this is where two quantum bits have some sort of link between them, or really it's more of a correlation. They are related in some way that can't be explained using classical mechanics, classical logic. And this is a thing that this is the thing that makes quantum computers really beat classical computers for large, complex problems. And then finally, interference, which is when your computer starts in some initial state, like the bits all have some value, and then you do various operations to them according to some algorithm. And there are two possible outcomes in this little thought experiment, say, and you could get to them by multiple paths, multiple sets of operations. And it's possible that some paths can cancel out other paths, even though they lead to the same place. This is a quantum mechanical property that doesn't occur in classical probability. It has to do with quantum mechanical probabilities. So there are some pathways where they cancel out, and some pathways where they add together, where you can. Yeah, and so in this case, outcome number one would not occur, and outcome number two would occur. And so this process of interference is one of the ways you, by designing your algorithm so the interference works correctly, is how you get to the right answer in whatever question you're trying to ask. You have a question?
Okay, so with entanglements, are all of the qubits in a system entangled, or can you choose, or does it matter?
It matters a great deal, and it depends. There are some paradigms of quantum computing where all of the qubits have to start out entangled with each other in a certain particular way, and you accomplish the steps of the algorithm by making measurements on those qubits in a certain sequence. There are other paradigms of quantum computing where all of the qubits start out unentangled with each other. Then you have to build up some entanglement and then do some sort of operations to them, like logic gates in a classical computer, and gates, or the quantum equivalent, which is slightly different. And in those cases, only some subsets of the quantum bits are entangled with some other subsets, and not all of them are entangled with each other at the same time.
So we can choose. Okay.
Yes. In general, you have some choice, and the quote right choice depends on what problem you're trying to solve. Okay, so how does that work? If you have some number of classical bits, n classical bits, here's an example of 3, they have some definite values. They contain n zeros and ones. There's some amount of information embodied in those bits, right? If you have n quantum bits, they can be all in superpositions and all entangled with each other in principle. And for reasons that I'm not going to go into right now, but because of quantum mechanics, to specify this state of the system, you actually need 2 to the n complex numbers. This is a combination of superposition and entanglement, which we just talked about. And so n quantum bits contains 2 to the n sort of values in it, which could be way bigger than n values like a classical thing. The issue is that when you measure those quantum bits, you don't get all of those numbers out. You only get n numbers out. When you measure the state of these bits, you get 0 or 1 for each of them. And there's n bits, so you get n zeros or ones. So whereas n classical bits contains n zeros and ones, and when you measure them, you will get n zeros and ones. N quantum bits contains 2 to the n complex numbers, which could be huge, but when you measure them, you still only get n zeros and ones. So there's this incredible amount of information here, and this is exponentially increasing. So if you have 10 bits, there are 2 to the 10 complex numbers in there, right? 1,024 complex numbers in only 10 bits. You have 100 bits, it's like 1 million different numbers. And that is where the power of quantum computing lies, in that huge space of numbers. And by doing measurements and various operations on the bits, you can get those numbers to interact with each other, so to speak. And then you have to do it cleverly so that the answer is contained in the much smaller number of values you can measure in the end. So if you have some initial state, you do some operations, you can in principle do that to all of those 2 to the n numbers, and you can change let's go back. You can change the superposition states or change the character of the entanglement shared between qubits, and that changes those 2 to the n numbers in some fashion that hopefully is intelligent. And then what you want to do is leverage the property of interference. So you choreograph things that for each wrong answer, the paths leading there cancel, while paths leading to the right answer reinforce. And so the right answer is the one that you measure. This is a quote of Scott Aronson, who's a computer scientist and quantum computer expert at UT Austin. So this is the property of interference. So superposition and entanglement enable the quantum computer to embody this huge space of values. And then interference is what you want to leverage so that after you do all these operations, the thing that you measure is guaranteed to be the right answer for whatever the problem is you're trying to solve. Question?
Will we touch on how we choreograph these so we get the answer that we want?
Not in this lecture. That is a very difficult problem because it's different for every problem.
Okay.
It's different for every thing you want to compute. There are a couple things that we can eventually go over. I think maybe Grover's algorithm, Grover's search algorithm is one of the simplest to see how it works. And you could program it yourself with some online tools. It's a pretty good, I think that might be the best way of seeing how this works. But at this point, it's all in the abstract.
Okay.
It's hard to do this well. Superposition and entanglement are very fragile. Here's a quantum bit in a superposition, and over time it has some time evolution, it changes. So that's this is very common. Most qubits do this in some form. So that makes things a little complicated. And then interference from other particles could cause that state to change. Or interference from electromagnetic fields nearby could cause those states to change. And what happens is that your superposition state could devolve into a definite state of 0 or 1. This is called decoherence. It's an unplanned interaction between your qubit and something else that mimics a measurement that was lost. When you measure the qubit, it goes from a superposition state to either 0 or 1 with some probability. And if that measurement occurs and then you don't get that information, that would be bad. And so if you have in your quantum computer, some electromagnetic fields are fluctuating, or the atoms of your qubits are interacting with other atoms that are junk that shouldn't be there, those are going to act like an unplanned measurement whose result is lost. This is the main problem with making quantum computers. How do you get rid of decoherence? So you start with some nice set of qubits that are all entangled in a great way, and then decoherence comes along and breaks that entanglement, changes some of the bits, makes some of them definite values, and that's a problem. Messes up whatever you really wanted to happen, which you're trying to do at the same time as decoherence is occurring. So what you want to do is isolate the qubit somehow from the devil of decoherence. And there's a couple different ways of doing that. One of the main ones is putting everything at low temperature, because thermal interactions act like measurements. And another one that often comes along with low temperature is putting everything in a vacuum. If your quantum computer is made of, say, ions or atoms suspended in some lattice, then you want them to not get bumped into by other atoms. And so the way to avoid that is to put everything in a vacuum. Right. So how do you actually make physical qubits? Well, how do you make classical qubits? Classical bits. Classical bit is either a 0 or a 1, and they have to be embodied in some physical system. For example, magnetic domains on a hard drive. If you have nowadays a lot of people have solid state drives, but when you had a magnetic hard drive, there would be a little regions of magnetic film on those disks that had a certain magnetization pointing this way or that way. One of them was a 0 and one of them is a 1. You can also have in a flash memory, you can have a kind of memristor that can store charge in a floating gate for a very, very long time. And you can put that charge in and out by writing to it. And you can also read it by running a current nearby and measuring what happens. So this is the 0 and 1 is embodied by the presence or absence of charge in this little region of some tiny microscopic semiconductor structure in a microchip. This is basically a USB flash drive, has zillions of these. But also, it can be something much more prosaic. In you know, history class in high school, middle school, you may have learned about Paul Revere's ride in the Revolutionary War. And he got a signal from the church in Boston across the harbor. A priest hung up lanterns to give him some information, and he was told 1 if by land, 2 if by sea. So 1 lantern if the British were coming to capture the Continental Congress by a land route, and 2 lanterns if they were going to try to go by a sea route. Basically, the revolutionaries had a spy watching the British, and then that guy hung up 2 lanterns here. Paul Revere and the other riders, there were several of them, saw that, gained information by that. Right, so far more prosaic than magnetic domains on a chip or a flash memory. Right, so bits can be anything. In fact, the signal has more than 1 bit in it. What's the other bit of information contained in it? What does it tell Paul Revere and his fellows? Sam, do you know?
Well, yeah, so.
You know, because we've talked about it before.
Yeah, and so if there's no lanterns, it's just they're not coming.
Right, no lanterns is they haven't left yet. Some lanterns is they're leaving, and then how many is what route they're gonna take. So that's a example of some hyperdense coding of information. A quantum bit, on the other hand, is a superposition state, and if you have seen any quantum mechanical nomenclature, you may have seen something like this before. If you don't understand this, don't worry about it. But this is how you mathematically represent the state of a single qubit. And it turns out that it is equivalent to a point on the surface of a sphere. That sphere is called a Bloch sphere, after a scientist who did some work on this sort of thing. And where it is on the sphere gives you information about its state, its latitude. I mean, like its north and southness, tells you, gives you information about the probability of it being measured to be a 0 or a 1. And the longitude tells you something about what's called the quantum phase, which turns out to be very important later on, but mainly when you have multiple qubits and they have different phases. And at this point, we don't have to worry about it very much. But suffice to say, a quantum bit can be represented as a point on a sphere, on the Bloch sphere. And there's a bunch of things that any physical qubit needs to have, which is called DiVincenzo's criteria. And you need to have all of these if it's going to work. You need a scalable physical system with well-characterized qubit. Scalable means you can make zillions of these that are all the same, and they're not going to be so vastly different that they won't play nice with each other. It needs to be a physical system because obviously it has to be embodied physically. You can't just think about it. That's not going to work. And a well-characterized qubit means basically you know how it behaves. It's well-characterized. You know how to manipulate it and what it does and how to measure it. You need the ability to initialize the state of the qubits to a simple fiducial state. This is like formatting your hard drive. Whatever the states of all the qubits are, set them all to 0. Got to be able to do that. Otherwise, they're just going to stay in some random state. That's totally useless. Number 3 is you need long relative decoherence time. So the decoherence time is a measure of how long it takes before decoherence has ruined your state. And so those, you want them to be long compared to how fast you can manipulate those states, basically. Depending on the system, some systems have really long decoherence times, but then also it's very slow to do any operations on them. So it sort of balances out. Other systems that you can make a qubit out of have really short decoherence times. That's not so good, but you can manipulate them very fast. And so the ratio is also important. You need a universal set of quantum gates. So a gate is some sort of operation like an AND or an OR or a NOT that you might do to some logical bits. And you need a universal set of them so that basically you have some few number of gates from which you can build any other possible gate. That's what a universal set is. And there's not just one universal set. There are many, many different universal sets. And depending on what physical system is embodying your qubit, it may be easier to use one or the other of those universal sets to construct other gates. Finally, you need a qubit-specific measurement capability. You have 100 qubits, you want to measure them all individually. You don't want to measure the first 10 and get their average value. That's not going to help you very much. So these are the criteria that you need. So anyway, there's a bunch of constraints on the possible systems that could be used to embody qubit. Now, I think the next bit is to talk about some of those ways. Yeah, there's a multiple of different ways to do this. A question.
Okay, so the more you utilize a quantum computer, the faster the computer's timer has.
Let me rephrase that question. Decoherence happens to your quantum computer even when you're not doing anything. Also, the more operations you try to do on those qubits, the faster decoherence happens, generally.
So the more you use it.
Kind of like the more you use it. But I guess I'm being more specific about that phrase. Like if you start your algorithm over again, and you're back to where you started. So the longer your algorithm is, the more decoherence will happen in it, even if you do it more quickly, generally because gates aren't perfect and they intend to induce some amount of decoherence themselves. So doing the operations that you would have to do, like running the lines of code that you would have to do, causes decoherence. General. Yes.
So after, let's say, these qubits have suffered from decoherence, what is the avenue for these qubits to then quote unquote recharge and become non-decoherent?
It's a good question. So generally, there's nothing you can do during that run of the algorithm.
Mhm.
You can't fix it.
Yeah.
You can restart the whole process. In which case you sort of reset all the states, you format the hard drive, so to speak, and rerun everything. And basically how good your qubits are, like how bad their decoherence is, and also how the fidelity or quality of the gates that you're going to do to it, the operations, how good are they? How likely are they to succeed? Those determine how long your algorithm can be. How many steps can there be in your algorithm? Because if it's maybe an algorithm works if it's 10 steps, but some more complicated algorithm, 100 steps. And there's no point in doing that because somewhere in there that all the qubits will have decohered. And so any measurement you do at the end will be totally random.
So my next question is, let's say, for instance, let's say my phone, for example, it works the same at 90% as it does 50%. Is that the same way decoherence works, or is there a point in time where decoherence affects the efficacy of the computer itself?
Yes. So it's not like your phone having 50% battery. Because it's more like, have you heard that cosmic rays can flip bits in a computer?
I would personally not, but okay.
This is a thing that happens.
Yeah.
Even your computers here are not perfect in their gates and such. And there is something implemented in them called error correction. Just the simplest version of error correction is in a classical computer, have 3 copies of every bit. If one of them gets flipped, you just measure them all and you go with the majority. This is a very simple form of error correction. It doesn't work in a quantum computer for various reasons, namely that there's something called the no cloning theorem. You cannot copy unknown quantum information. And so also if you measure those bits, then you've tanked your algorithm. You need to carefully not touch anything in a way that measures them while the algorithm is happening. Whereas it doesn't hurt a classical bit to be measured. And so imagine if you didn't have error correction in the classical computer and your various gates are not perfect, then as you do them, you're starting to scramble all that information. So maybe it's being bombarded by cosmic rays. And those are starting to randomly flip bits as time goes on. That's decoherence. That's a sort of classical decoherence.
Okay.
Yes.
So could you elaborate when you refer to the algorithm or an algorithm?
An algorithm is some sequence of operations done to the ensemble of qubits that make up your quantum computer. So, when I say something like an AND gate or an OR gate, do you know what this means?
Yes.
Like in a classical computer, you have 2 bits, and doing an AND on them produces an output that is 1 if both of the inputs were 1, and 0 if any of the inputs were 0. That's an AND gate. And so you would, in a classical computer, that's very fundamentally, in some very basic sense, all of the operations like running code on information stored in bits. That's how it works. Do these various gates on the bits. And so an algorithm is some sequence of gates on the bits in a classical computer. And the same thing is true for a quantum computer. The algorithm is some sequence of gates or operations done to the qubits. And depending on what sort of problem you're trying to solve, that algorithm will be different. Right?
And to make an assumption, because you cannot measure the qubits, and it's important to keep or halt, what was the word?
Decoherence.
Thank you. Decoherence. So you can trust that your algorithm will see itself through.
Right. Right. You want to avoid decoherence if you can. And you want your gates to not induce decoherence themselves also. Yeah. And so that's the main problem. That's the main difficulty with quantum computers, is that decoherence is impossible to avoid entirely, and difficult to avoid enough so that a quantum computer can do something useful before its qubits decohere into total randomness.
Does that mean that our current ways of making quantum computers, like, they're a lot more fragile than your average computer?
Absolutely, every quantum computer, the information stored in it is like millions, zillions of times more fragile than that in a classical computer.
Okay.
Yeah. Simply put, that's it. Okay. What are your other questions so far?
You talked about encryption breaking. So have we gotten to that point, by the way?
No, I haven't gotten to that point.
I mean, have as a
No, well,
humanity.
we
Actually,
factored the number 15.
yes, I actually worked on a team of people that was researching this to answer your question. We factored 11 and 15.
Okay.
So not something that we're gonna be using to break like 256-bit RSA, but we're getting there. We've shown
I
that
see.
it does work, but we just need bigger computers.
And if we get to that point, will we then have another form of, I guess, encryption or security?
Hopefully, we have another form of security long before that point, because you can store information now to decrypt it when a quantum computer is eventually available. So you can imagine China and the US are storing each other's intercepted encrypted communiques, and they can't be read now, but they could be read in principle in the future when a quantum computer gets built, and that could cause some problems.
Wow.
Right, but we can factor the number 15, which is not very impressive. So the factoring is part of, if you could factor a very, very large number into its 2 prime factors, then that's equivalent to letting you break encryption in the modern age.
Okay.
Yes.
So this is kind of weird, but there's a type of encryption that relies on a wall of lava lamps.
Oh, I've seen that.
Where essentially, because we know so little about the physics of like lava lamps, that it's completely random, and so there's just a camera picking up all these lava lamps and then converting that into an encryption somehow.
Okay.
Do you think it could break that specifically, or would you need or would we need to know more physics?
I would have to know how that encryption algorithm works.
So
Yeah.
it's actually just RSA, and the lava lamps are just a random number counter.
Okay.
So
That-
it's
Yeah.
no.
Okay,
It's the same thing functionally as
Okay.
what we can do, so that would not protect you.
Okay, so we would be able to break it.
Yes, you would,
I'm
yes.
not sure how the random number generator actually works in RSA, because RSA you need,
So
a
well,
particular.
because computers can't make
typically-
random numbers. so-
typically they can't, but we make chips that can get very close to random numbers. And it's called a TPM chip,
Yeah.
trusted platform module. We use that to generate RSA currently. That's not ideal because it's still not random. The lava lamps are functionally random. So yes, but what we're doing with the quantum computer, the Shor's algorithm is finding that random number, so it kind of doesn't matter.
Okay,
Just really quick, could you explain what RSA is?
So you take, on your computer, you have what's called a private key. You generate two exorbitantly large random numbers that are prime. Two exorbitantly large prime random numbers, so there's no factors. You multiply them by each other and you give everybody else that product. And you say, if you want to contact me, you run your message through the product of my two prime numbers. And then nobody can decrypt it except the person with those two prime numbers. So what the quantum computer is doing is it's saying, okay, you've given me your public key because I actually need that to send you anything. But now I can find those two prime numbers and also decrypt anything anybody else sends to you.
I see,
Yes,
interesting.
sorry, I don't
No,
wanna
that's good.
steal
No, it's
steal the
good.
spotlight.
That's totally fine.
I spent
Listen,
time working on this, so.
That's great. That was a good explanation.
It's very helpful, thank you.
Yeah, encryption. Two-factor, yes, this sort of asymmetric encryption is based on a math problem that is easy to do in one way, but really, really hard to do the other way unless you have the key. And the thing that quantum computing could do is let you take that public information and find the key. Which otherwise would take a huge amount of computational expense to find.
It's a bit out there, but it's a bit like the Zodiac Killer. Because because the reason it's so hard to decrypt what he's written is because he's made his own weird I guess encryption, lack of a better word. And it's not exactly that it was hard to make, but just because we don't know what he was trying to do with it, and his methods is it's like security through obscurity.
Uh-huh.
Yeah.
Yeah.
Does that make sense?
I know what security through obscurity is. I don't know enough about the Zodiac Killer to say anything intelligent on that.
Well, and sure, I'm just trying to say, it wasn't very hard to make his ciphers, but because we don't know the exact way he did it, that's why it's so hard to crack them.
Okay. Let's get back to this. I guess there's several different ways to make a quantum computer physically. One of the main ones is superconducting circuits. Here's a close-up of some superconducting circuits. Each of these little squares is about a few millimeters on the side, and this is what's called colloquially the golden chandelier of a superconducting computer. Tiny chips like this are inside there, and then this whole thing is cooled down to a few millikelvin above absolute zero in order to try to get into one, make everything superconducting, and then two, to get rid of decoherence. This is one of the most mature technologies. It's the one that IBM and Google have invested in. There's also trapped ions. So an ion is an atom where it has one electron or one or more electrons removed or added to it, so it has an electrical charge. And they can be trapped by tiny electrodes, and then atoms turn out to be, they have the properties of qubits. They can be in superposition states of different energy levels, different orbitals. You can also do a very similar thing with trapped atoms. So an atom is neutral. You can't use electrical charges to hold it in place. Instead, you can use lasers, and this is a schematic cartoon of the sort of potential energy pups that looks kind of like an egg crate, where atoms could be trapped, which these are created by crossing laser beams in space, and then the atoms can get trapped in there. And then finally, there is the possibility of doing it with photonic circuits, where photons are representing the qubits, and they interact, quote unquote, by interfering with each other in some circuit of little wires that carry the light. Like an electronic circuit has metal wires that carry electrons, a photonic circuit has little clear wires that carry photons and carry light. Yes,
How big are quantum computers?
depends on what you mean by big. This thing is, I don't know, could be 3 or 4 feet across and 10 feet tall. This the golden chandelier. But the actual business part is the size of a microchip.
Oh, okay.
But it needs all this other stuff associated with it to work. Like in my laptop,
Yeah,
the microchip that's doing most of the thinking is only this big.
yeah.
But it needs all this other stuff
Mhm.
attached to it to really do the job, right?
Do you think they will get smaller, like the actual like whole?
I hope so, because otherwise it will be impossible to scale them to the
Yeah.
size we need. One of the main problems with this kind of thing is that you can see all these little wires and stuff in this picture in the lower left. Those are all various voltage controls and microwave microwave transmission lines that deliver the control signals to the actual quantum chip, which is like this thing in the upper left. And if you make a bunch more chips, a bunch more qubits on that chip, it's still pretty small. You can make a lot of those, but then you have to make many more of these wires and such, and it just gets to be a big mess. Most of the effort in constructing this sort of computer is in doing that stuff, and it just takes up so much space. So scaling that, finding a different way of scaling that kind of the ancillary technology that is not a qubit per se, but this other stuff. Finding ways to miniaturize and scale that will be a big effort in making the quantum computers smaller and thus able to have more qubits. Yes.
So how big is a qubit? And or do they vary in size between different models?
Well, they definitely vary size between different models. So in a trapped ion or trapped atom computer, the qubit is the atom or the ion. So it's basically as small as matter could be. In a superconducting circuit, the qubit is some few microns on the side. It's sort of a microwave resonator with a special kind of superconducting junction inside of it. And that can't be made any smaller because of the wavelengths of light involved, basically. They operate at certain frequencies. A certain frequency of light has a certain wavelength, and then the object that interacts with it have to be about the same size as that wavelength. So it can't be any smaller unless you have a way to make it at a much higher frequency, which turns out to be difficult. Photons also have a sort of limiting size. They are similarly about the size of a wavelength. Their wavelength is much smaller than the microwave wavelengths used in superconducting circuits, so they can be smaller. But also a photon never stops moving, and so a photonic qubit is always going to be traveling at the speed of light through whatever circuit is going on that it's in. So all of these things have very different challenges associated.
They're all spherical though.
Let's see, they all can be represented mathematically by a point on a sphere.
Okay,
That's not the
okay,
same
yeah,
as
yeah,
them
that's
being
what I meant,
spherical.
sorry.
Yeah. Yes.
So a little out of the way. But I'm a music industry major. We just talked about, waveforms of audio.
Mhm.
I'm guessing that the wavelengths and sizes of photons are a lot different than of sound traveling.
Yes. Right. It has to do with the speed at which the wave moves. What instrument do you play?
Saxophone.
Saxophone. So the saxophone has some lowest possible note, right? You close all the holes in the saxophone.
Yeah.
And the air column inside the saxophone vibrates at some frequency. And it turns out, let's see, the saxophone is a closed and open tube. The length of the saxophone is about half of the wavelength of the sound that comes out when you have all the holes closed. And that's, about a meter on that order, depending on, if it's say, tenor sax, something like that.
Yeah.
Yeah, and so it's because the frequencies that you want to play a note at have to be hearable by a human, and so that limits the frequency range. And then the speed of sound in air has some speed, and they have a particular relationship, frequency times wavelength equals the speed of the wave, right? And the speed of sound is much lower than the speed of light, no surprise to anybody. And so the speed of light can is huge. Thus, you can have a much smaller frequency. Sorry, what am I saying? A much smaller wavelength.
Okay, yeah, because I just wrote it down here, wavelength equals velocity divided by frequency.
Mm.
So, yeah, velocity being very, very large, so,
Exactly.
okay. Interesting.
Okay. So I've got a couple of examples of how these sorts of things could be used as qubits. I'll start with photons, since that's the one that I'm interested in professionally. And I think it's easiest to understand of these examples. So a photon is always moving, and so they're sometimes called flying qubits. They are the most likely thing to be used in any kind of quantum communication, quantum networking scheme, because it's, you know, you can't stop a photon from moving. It would be very difficult, on the other hand, to move an ion from one place to another, or a superconducting circuit, or to send a microwave photon. But an optical photon, that's how we carry information in the internet nowadays with optical fibers. So that's the likeliest way we're going to have information transfer across a quantum internet, some hypothetical quantum internet. And the qubit could be embodied by any of the properties of a photon, which include its presence or absence. You could have no photon be a 0 and yes photon be a 1. There's problems with that, which I'll talk about in a second. Yeah, so here's what's called single rail encoding. You can have the presence of a photon be a 1 and the absence be a 0. But the problem with that is that what happens if that photon gets scattered out of whatever wire it's traveling in? Then your 1 has changed into a 0. So you think it's a 0 where actually it's an error. There's dual rail encoding where you use 2 wires, and which wire the photon is in tells you whether it's a 0 or 1. This time, if you don't detect the photon, you know there's a problem. You could use the polarization of the photon to encode information, its wavelength or its frequency, the spatial mode, which is really its shape. What is the shape of the vibrating wave as it's going? Its timing. You could have early or late relative to some clock be the 0 or 1. You could use some quantum squeezed state, which turns out to be one of the most promising methods, but is a little difficult to describe, so I'm not going to at this point. Here's an example of polarization. This is an animation of polarization, some linear polarization or some circular polarization. And it turns out that polarization has, I mentioned this block sphere that on the surface of which is some point on the surface of the block sphere is represents a qubit's state. And there's an equivalent thing for light polarization, except the sphere is called a Poincare sphere because it was developed by a different scientist much earlier. But so it's mathematically equivalent to that. You can also have entanglement between photons. Don't worry about this too much, but basically you can split one photon into 2 photons, and if you do it right, they will be entangled with each other. And so that's in fact, the first experimental measurements on entanglement done with photons, because it's way easier to make entangled photons than anything else. Nobody had any good ideas about how to make other things entangled at that point. That was in the let's see, late 70s, early 80s. When this was done. This is what the Nobel Prize was given for a few years ago. Entanglement. Question.
You can split photons?
With difficulty, you can split photons.
Wow.
You can have one photon with some amount of energy get split into 2 photons with whose energies add up to that one energy.
I see.
But it requires a certain special kind of crystal, and it is difficult to do for a number of reasons. We have a setup somewhere in the building that can do that.
Wow.
And I hope we'll be able to get to play with it at some point this semester. So what are the advantages of photons as qubits over other things? Well, they have an order of magnitude greater range than any other mobile qubit. You can move an ionic qubit a few millimeters, but you can send a photon hundreds of kilometers. They don't have any thermal noise even at room temperature, which is nice. Remember, many of these things have to be cooled down to very low temperatures. But it turns out that if you use optical range photons, but kind of we can see, it turns out that the temperature is sort of irrelevant. They have so much energy compared to the average thermal energy at room temperature that there's not going to be any thermal noise. They have little to no dephasing, which is related to their phase skipping. And photonic circuits can be created by lithography, which is the same process by which you make a microchip with literally billions of transistors. And so you can scale the photonic circuits in principle very easily to the millions. So that's a good advantage. The disadvantages are the range is not infinite. I said hundreds of kilometers, which seems long, but actually, it's only from one city to maybe a neighboring nearby city. It's not that far. And there's also loss along that way that contributes to decoherence. I described it talking about single rail encoding. If that photon disappears, you think your 1 has changed into a 0, whereas really it's an error. So that is a problem. If photons get lost, it's equivalent to decoherence. A big problem is that photons don't interact with each other. They only interact with matter. And so if you want your photons, which are your qubits, to interact with other qubits, basically to do some kind of logic gate, you need one photon to interact with some matter, and then that matter to be changed in a way that affects the other photon. So matter needs to mediate the interaction between those photons. They otherwise don't see each other, pass right through each other like ghosts. And those matter-mediated interactions are extremely weak. This is why it's difficult to make entangled photons, because it's basically a matter-mediated interaction. It's very weak. And so you need really intense laser pulses and special crystals, and it doesn't happen all the time. So it's hard. Yes.
So is it just coincidence that photons that are at the frequency that we can see have these types of properties?
I wouldn't call it coincidence.
Because I mean, light we can't see would not have that kind of advantage.
Well, no, there are other lights that we can see that we cannot see that have similar advantages, but they also have disadvantages. In fact, the photon range that would be most ideal is what's called the telecom wavelength range. That's the range that goes in our optical fibers to carry information across the internet. That's infrared light, you can't see it. So it's not technically optical, but it's not that different. It's only about, say, half the energy per photon of visible light photons. All right. So how would you use a superconducting circuit as a qubit? The main magic inside a superconducting qubit is what's called a Josephson junction, which is two superconductors separated by some insulator or normal conductor, or maybe just a gap. This is called the Josephson junction. And the reason it's important is not obvious. But what happens is that in a superconductor, you probably know that current can travel without any resistance. It's a perfect conductor. It has some other properties as well, but one of the things is perfect conduction. And if there's a gap, well, the wires don't touch each other. What should happen? There should be no current, right? However, because if the gap is really, really small, the electrons can tunnel through the gap. This is a quantum mechanical process where they basically can go from one superconductor to the other and cross that intermediate space. Whereas in a classical picture of what's going on, you wouldn't expect that to happen. And they can tunnel across this gap without any voltage difference. So it's like it's kind of not even there. This is the circuit symbol. This X through a line. What is that? How is that helpful? There's a relationship then between the current going through and the sort of the phase of the quantum mechanical wave of the electrons. on either side of the superconductor. There's a particular difference in the phase going across. And you don't really have to understand this right now, but this is basically the magic sauce, a nonlinear interaction. And you can use these Josephson junctions to construct some circuits. Here is a capacitor and a Josephson junction and a voltage source. And the capacitor is basically two plates. This is kind of like a very large Josephson junction, and its behavior changes, but this is a very small junction between two superconductors, and the rest of these wires are all superconductors. And this makes a little separate section of here, and by tuning this voltage, you can, do I say it? Yes. You can choose this voltage U to have a superposition of 0 or 1 extra Cooper pair of electrons inside the box. A Cooper pair is two electrons that have sort of bonded together inside a superconductor, and part of what makes a superconductor conduct with no resistance. You don't really have to understand that either to appreciate this, but basically you can set up a quantum mechanical superposition of different numbers of electrons inside that box, and that could be your 0 and 1. You can also, this is called a charge qubit, where the state of the qubit is, less charge or more charge. There's also what's called a flux qubit, where you wrap the superconductor into a ring, except it's broken by a Josephson junction on one end. And then you put a magnetic field through it, and magnetic field going through this conductor causes current to flow. And you can choose that current, you can choose this flux to be just right so that the current in this loop is in a superposition of going clockwise and counterclockwise. That's a very weird thing, but quantum mechanics has some weird non-intuitive results. This is a flux qubit, and there's a couple other flavors of qubits which are actually more commonly used nowadays, but are even more complicated to explain, so I'm not going to try. What are the advantages of superconducting circuits? Well, that's the most mature technology, and there's vast investment in it compared to all of the other varieties. You could do multi-qubit interactions via microwave circuits, which is a sort of simple process technologically. These are also created by lithography, like silicon chips, like microchips in your computer, so they're easily scalable. And you can manipulate them with voltages and currents, like other circuits. So electrical engineers and people who are familiar with circuits just immediately sort of understand these with less investment of effort. What are their disadvantages? They have to be super cooled, 10 millikelvin, 10,000th of a Kelvin by absolute zero. Takes $1 million just to make something that can get that cold. That's not even including the actual quantum computer. They're stationary, and microwaves that are the way these interact with each other, they don't travel very far, so you're not going to send a microwave from here to another city. And it might be difficult to scale the classical control voltages and currents. This is what I was talking about when we were looking at the golden chandelier. There's all these wires coming down. At some point it gets infeasible to have a zillion wires. So that might be hard to scale. And they're also relatively big compared to the other kinds of qubits. Yes.
If you had to choose a way to build a quantum computer, what way would you use? Would you use semiconductors, photons, or like the other ones that were talked about?
There is no right choice at this point in history. And that's why there are people working on all of these. They all have disadvantages and advantages, some of which I've enumerated here. And it means that there's no winner yet.
Mm-hmm.
There's nothing that's like, that's the right answer. All of you doing this over here, you just stop because there's no point. So you know that our microchips are made of silicon, perhaps you know this. Another equivalent and arguably better semiconductor is gallium arsenide. It would work better in certain ways. And if we made all our chips out of gallium arsenide, they might be better. But it has problems of its own. It's sort of more difficult to purify, and fabricating the kinds of circuits that we need is not as easy. And the most important part is that there's 100 years of effort in the silicon industry already.
Yeah.
So silicon is super mature.
Yeah.
Whereas gallium arsenide has always been a side project for that same amount of time. So there's a sort of analogous situation.
Could that be done with a high temperature superconductor or would it be too much interference?
Oh, that's a good question. I haven't thought about that before, but I'm not sure that the advantage is obvious because the frequencies at which these guys operate means that, which means that they operate at kind of low frequency, microwave frequency. And thermal energy at room temperature is sufficient to spontaneously create microwave photons, microwave frequencies. So even if your superconductor worked at room temperature, because it was a high temperature superconductor, or even liquid nitrogen temperatures, 77 Kelvin, I think you might still have to refrigerate it down to preposterously low temperatures to avoid thermal noise. That's my off the top of my head answer. I don't know if there's some subtle thing that would mean you could use that technique. Yes.
Now, does it take $1 million to create something that can get, or a system that can get that cold, or to make something that cold in the first place every time?
It's more like making the system that can get something that cold.
Okay.
To
When you
actually
have
get
it,
it works. Yeah.
Okay.
Then it just takes a lot of electricity to get it to run it, to keep it cold. Okay. Trapped atoms or ions as qubits. These are sometimes called nature's qubits because their properties are determined by not by human design but by nature, which is nice because they're all the same. Every rubidium atom is the same as every other rubidium atom. So there's a couple ways of doing them. Electronic qubits, which are, you could have two different states of some outermost electron, the valence electron. It could be in some ground state or an excited state. You've probably seen a cartoon like this before. It's not really what it looks like, but it gets the idea across, where a photon, an electron could jump from one orbital to another orbital, and those could be your two states. You could also have what might be called hyperfine qubits. They are related to the relative orientation of the quantum mechanical spin of an electron and the nucleus, and they could be oriented in the same direction or in opposite directions, and that could be your 0 and 1. And these two things are different flavors of the same kind of system, and they have their own advantages and disadvantages. So what are the advantages of atomic qubits? They have the longest coherence times of any qubit platform by far. They couple to photons because an electron jumping from some outer shell to a lower shell will emit a photon. And it can also absorb a photon and go from some inner shell to some outer shell. So that's good. It couples to the quote flying qubits, so they could be used to communicate information between ionic qubits. And atoms and ions of the same type are guaranteed to be identical, which is great for scaling up. You have 10 atoms, they're all the same. You have 10 million atoms, they're still all the same. Whereas 10 million superconducting circuits will all be slightly different and need to be tuned to be the same as each other to interact. What are the disadvantages? They have to be isolated in vacuum and electric and magnetic fluctuations. So that's some experimental challenges. At least 2 Nobel Prizes were involved with just getting atoms to hold still. That's not including using them as quantum bits. So it's a big effort. Whereas superconducting qubits aren't going to run away. They're just right there all the time. They have to be tracked and kept in one place. That's difficult. They can also escape. This is a technically decoherence, even though it's more like your computer is falling apart as it's trying to work. And then you have to sort of put it back together again to restart the algorithm. And the coupling to photons, even though it exists, it's not very efficient. So that's not as good as you would like it to be. Oh yes, how do you hold them in place? This is an example of a somewhat homemade version of what's called a Paul trap. It's got 3 electrodes, a ring and 2 spheres on top and bottom, and the 2 spheres are held at 1 voltage and the ring is held at the opposite negative voltage. And an atom, an ion really, an ion in the middle there will experience some potential energy that looks like this graph over here, looks like a saddle. So it confines it in one direction, but it actually tries to push it away in the other direction. So how do you get it to stay in one place? Well, you rapidly oscillate the voltages so that that saddle flaps around back and forth, back and forth. If you do this the right frequency, then the atom will actually not be able to escape. Yes, question.
And the saddle is a representation of potential energy?
Yes,
Okay,
in this case, in just 2 dimensions, but the same
okay.
in. it happens
So,
in 3
okay, so it doesn't literally look like this, it's just a reasonable way that we can,
visualize what the dynamics are. Yeah,
okay,
so there's no, like, you can't see this moving.
right.
And it also happens at much higher frequency than this little animation's showing. Okay. Oh yes, here's a picture of, these are actually dust particles, but it shows the method by which ions could be trapped. These are the edge of 2 razors, the top and bottom of the image are the edge of 2 razors, and they have a voltage applied across them, and there's depicted here a couple more electrodes that enable this sort of Paul trap. And here's a bunch of charged dust particles that have been trapped in a little line, and they are separated from each other because they're all identically charged and they push each other apart. So that's kind of nice self-assembling of your quantum computer. The link is not appearing here, but this is from a YouTube video where somebody made this in his garage, literally. That's not a quantum computer per se, but it gives the idea about how you would trap ions. Right, so that's all theoretical stuff, but you can play with a real quantum computer. This one, or one that looks very much like it. You can see this is the golden chandelier, you know where the name comes from, looks like that. The IBM Q experience, quantum experience, is a publicly available 5-qubit system, looks vaguely like this, and you can access it via the web. There's something called the quantum composer or circuit composer. It looks like this. It's a drag and drop interface where each of these horizontal lines represents a qubit, and each of these little boxes, which you can drag down here, represents some operation to be done on that qubit. And the one that's depicted here takes these first 2 qubits and entangles them and then measures it. And it took me about 10 minutes to do that at some point in the past. When I first did this, it took me longer to create an account than to entangle 2 qubits. And these other qubits aren't doing anything in this particular thing, but so this is pretty neat. You can do it on a real quantum computer and build up some algorithms, you know what you're doing, and test them out. And there are bigger systems. I think they have a 16-bit one, but you have to subscribe and it costs money. But it's useful for researchers to be able to access this kind of thing because many more people want to play with a quantum computer than have the money to build one. And so IBM makes this thing available for researchers, and this one's for anybody to work on. Yes.
And okay, so for this computer, they basically just have it open to anyone that on any part of it, you'll tell it to do something and it'll do it.
Yes, sometimes you have to wait for a queue because other people want to do things too, but yeah.
Okay. And okay, so as in there's only 5 qubits available?
This computer has 5 qubits in it. And so you can do any kind of algorithm that involves up to 5 qubits.
Okay.
Yeah. Which is not a lot, but it's enough to sort of experiment on things.
Is there a theoretical good number of qubits for in the future use for practical tasks?
Yeah, millions. But we're far from having quantum computers that can do things that can't be done with classical computers.
So we're not sure how to get that many qubits to do what we want yet. I see.
Yeah. We have supercomputers that can simulate the entire behavior of this quantum computer, sometimes faster than actually programming and running the quantum
Oh, yes.
algorithm.
5 qubits, you can almost do that with your hands on paper. Your laptop can simulate probably 30 qubits without running out of memory. Uh, 50 qubits would give a supercomputer a hard time. So once we get to having quantum computers that are regularly more than 50 qubits with high fidelity gate operations and a sort of good interconnectedness between the bits, meaning that they can all interact with each other, then you can start simulating things on the quantum computers that cannot be simulated efficiently on even a really big supercomputer.
Okay, so we can simulate qubits and their behaviors up to a point to which it would just be better to use qubits.
Presumably. The trouble is, once you get to that point, how do you check what's happening? They have to be very clever about algorithm design,
Okay.
because there's no way to check it.
Because you can't measure it.
But you can measure it, but you can't simulate it on some other thing, so you don't know what's sort of necessarily happening on the way. You can measure the results from that quantum computer, and if you are smart, you would have designed your algorithm in such a way that the answer is easy to check, even if the answer is difficult to find. Like factoring one large number into its prime factors. It's very easy to check. You could do it with a calculator. But actually finding those factors when you don't already know them is super, super hard. That's why it's used in encryption.
So it's also trusting the algorithm to give you a right answer.
Yeah.
Okay.
You need to design your whole experiment in such a way that you can verify somehow that whatever gobbledygook the quantum computer outputs is right. Because if you have no way of verifying it, then what's the point of doing it here?
Right.
Yeah. Okay, we're almost done here with my little presentation. So there's a number of common misconceptions that the public and even the scientific science writing community has about quantum computers. And so I'm going to point them out here so that you can see them when you read stuff about quantum computers in the future. Will the next iPhone be quantum? By the inflection of my voice and probably what we've gone through so far, you can tell the answer is going to be no. No, your next iPhone, no iPhone will ever be quantum, not just the next one. Quantum computing is only for special tasks. There will never be I can't imagine, and nobody is making the argument that there will be some situation in the future where classical computers will not be needed anymore. Everything will be quantum. That's not what anybody's saying. These will almost certainly be specialty devices for special tasks. Quantum computers try all possible number combinations at once, also known as quantum parallelism. This is a more subtle one, and it happens a lot in science journalism, but it's not quite right. Operations you can do can hit all of the qubits, but which outcome is measured at the end depends on randomness. And so it's not like, I want to decrypt this message, which requires me to factor this number. And so I will make my qubits into a superposition of all possible numbers and then multiply them together, and I'll find the ones that work just by magic. That's not how it works. The quantum parallelism is a concept, but it's not this computers trying all possible number combinations at once. Remember, some number of qubits embodies 2 to the n, where n is the number of qubits, 2 to the n numbers. So that could be a huge number of numbers. And that is where the quantum parallelism comes in. But at the end, you can't measure all those numbers. You can only measure n of those numbers. And so which outcome is measured depends on some randomness. And you need to intelligently design your algorithm so that the right answer is the one that comes up. Finally, this is about entanglement more so than quantum computing, but they are related. Changing one entangled particle will induce a change in the other, which is not true. Entangled particles are related or correlated with each other, but they're not tied in some way where you change one, it'll change the other one. You can't force some particular outcome of a measurement on entangled particles. So entangled particles can't be used to do, say, faster than light communication. If you have an entangled particle and you go to another solar system and I have a particle that's entangled with your particle, we could measure our particles and then to each other, unless we communicate later, the outcome will be random. But later on, you come back from your trip to another solar system and you compare your measurement to mine, you will see that they are related to each other. They will always be the same thing. They will have been the same just that one time, but once you measure it, the entanglement's broken. If you went to that faraway solar system and then you did something to your particle that's entangled with mine, and then you measured it, and then you came back and we compared, well, it might be that they're totally unrelated because you did something in the middle. So it's you doing something to your particle doesn't affect my particle. It's only that measurements on entangled particles are correlated with each other. So this is not specific to quantum computing, but it is a quantum mechanical phenomenon that's often misunderstood. Yes.
Okay, so you said, okay, you go to their solar system, and you might do something that would break the entanglement. What constitutes something?
So, measuring breaks the entanglement. But you could also, let's call it, say colloquially, you could flip the particle on its side. And when you measure it, now you're measuring a slightly different property of it. And that property is not correlated with the property that I'm measuring. How do I think of an example that's easy to digest? If we had, I want to bring up spin. If we had two photons, you had one photon, I had one photon. Their polarizations were entangled in such a way that when they were produced, they always had opposite polarization. And they go off in different directions, those photons. And I measure one and you measure the other one. Whatever polarization I measure, the issue is that there are different ways to measure the polarization. You can measure the polarization, is it vertical or horizontal? That's the question to ask. Then one of these would be 0, the other one would be 1. You could also say, is it diagonal or anti-diagonal? 0 and 1. Or is it right circularly polarized or left circularly polarized? That would be 0 and 1. And so depending on the choice of measurement, the results of our two measurements will or will not be correlated. If we make the same choice, I'm going to measure vertical or horizontal. You will also measure vertical or horizontal. We'll always get the opposite result.
Okay.
If I decide to measure circular, right circular and left circular, and you measure vertical and horizontal, our results will have totally no relation to each other.
And then being able to be broken.
And when we measure it, the entanglement will be broken.
I see.
Okay, so let's summarize. Quantum computing will be used on a subcategory of very hard problems. The likely first thing will be simulating complex quantum systems. It leverages the quantum phenomena of superposition, entanglement, and interference in some clever way, if you do it right. Quantum computers might be made of superconducting circuits, or trapped atoms or ions, or photonic circuits. And some players in the field and industry are IBM, Google, Intel. They're all doing superconducting circuits. And then there's a bunch of startups at Yale, University of Maryland, Duke. They're doing variations of ionic or atomic qubits or photonic qubits. And watch out for common misconceptions in the lay literature about it. And thanks for your attention. So, what are your final questions?
There's a lot. It just kind of. Just gotta search my brain and pick ones out.
All
But
right.
anyone else can go, yeah.
Anything from over there? Sam, anything you want to say as president of the club before we adjourn?
So, thank you all for coming. I'm Sam, as the president. One thing I will mention, I kind of brought it up to is, and a few of you guys, is, we are looking for another officer. And, it's a pretty casual club. You wouldn't have a whole lot of responsibilities, but if you'd like to kind of get into a leadership role and intro into it, let me know. And we might have another election for the next officer. Okay.
Okay.
It's not all now.
Just about the club,
Yeah.
so are we officially part of the club or do we need to join still?
So it's just on Engage, just request membership, just for the WVU on technology.
Okay.
It also make it way easier to communicate with you guys, just raise the email on that way. That's it, really. We don't have any really requirements or anything. Just kind of, just come to a few meetings. And whatever.
Interest and attendance, that's the requirements for club membership.
Yeah, say be here and then we'll consider you a member, but.
You want to talk about the next meeting?
So. Obviously, this time works for everyone here. I got a few emails about this, well, maybe a one-time thing, I'm not quite sure about, I couldn't make it this time. Now, I guess we haven't fully decided, we're likely doing bi-weekly meetings every 2 weeks. Okay, so we wouldn't meet next Wednesday, but the next Wednesday from 5:30 to 6:30. Does anyone that wants to be there have super concerns about that right now? Okay. So I'll ask people who couldn't come today, if just a general conflict with it. See if we can change anything for them. But so if it's viable, we'll also be recording meetings when we can. That's not always gonna be feasible. Yeah, so some activities really won't work that way. But also I'll mention, I think we've got a few specific activities that Dr. Flagg has used, I think over the summer for a quantum information science thing. To kind of get everyone more familiar with some of these concepts like entanglement and quantum mechanical things. That's our plan for the next week.
Right? Gonna do these games,
Yeah, I guess quantum games.
so there's some
Yeah.
board games that represent some of the dynamics of quantum of qubits and or quantum computers. So it'll be sort of fun, low key, you don't have to know anything, but you'll get to learn something in the process, and also it's interesting.
So it's called WVU Quantum Technology.
Yes.
I mean, the icon's like a little fancy cyber circuit board. Yeah.
And I'm sorry, how will you I guess communicate
So, email,
email?
yeah,
Okay.
so obviously I have everyone in this room's email, probably,
It's also that Discord server, right? I
yes.
think you mentioned it in the email that we, like, I joined it, but I didn't see that anyone else had in like a
Oh, yeah,
while.
it's,
Yeah, it's,
we can boot it back up.
we should boot it back
Okay.
up, so you should. Have you joined?
I'm part of it, yeah,
Okay,
but I'm not sure who's the moderator of it.
I mean. Dylan is the one who created it, but he's long graduated.
Yeah.
I'm also a moderator or
Okay.
something, so.
And then
Maybe you want to make a new one so you can have ownership.
we'll see if we need to.
No, I think I have ownership
That
or
makes sense.
control at some.
Yeah,
Here's a good general question. Is there a difference between, okay, quantum mechanics and quantum physics?
No,
No, they're the same thing.
yeah,
Okay.
quantum mechanics is the,
so,
I don't know, the kind of. Sub area of physics devoted to quantum stuff, but he said quantum physics,
They're interchangeable.
they're mostly interchangeable. I think. Yeah. Okay, oh, yes.
Sorry, I had a question about the club. I was wondering what type of, if you do any like big research projects or anything throughout the year like that.
We have not before. We've done in the past a various seminars, usually virtual, where industry researchers have given us presentations about some aspect of quantum computing. We've also had students learn the quantum computing code language, Qiskit, which is developed by IBM for controlling their computers, the one that I talked about in here. And there's a Qiskit certification exam, which some people have taken. But that, having tried this one time, it seems like that's maybe more advanced than the membership of the club is interested in at this point.
Okay.
Yeah. We have a new-ish kit of experiments that involve quantum optical phenomena, basically photons that where you can measure their quantum mechanical behavior in the building now, and I'm hoping that sometime later this semester we'll be able to go play with that some. But I would say that the club at this point is not in a position to do research per se on quantum mechanical stuff. Maybe in the future, that would be great. But, yeah.
I guess a pretty general question. An idea I've heard a bit in, I guess, popular cultures, that can regard quantum mechanics. Is it true that when you measure something, well, quantum, does that bring it into existence, or has it always existed?
That is a question that is unanswered.
Okay.
So there's something called a measurement problem in quantum mechanics, which is maybe a rephrasing of what you just asked.
Okay.
Which is what does a measurement do? It seems like a measurement is different from a lot of the other dynamics of quantum mechanical systems, but why and how is a measurement different? And it boils down to, so far, a matter of philosophical interpretation of the rules of quantum mechanics. Nobody has quite yet developed a testable theory that says this is what, quote, really is happening. That's not quite true. There, in the sort of 60s, there was Bell's theorem, which did result in a testable proposition